Sometimes acids have more than one acidic hydrogen. So we'll consider one of the most common examples, sulfuric acid. Sulfuric acid has two acidic hydrogens. When you add sulfuric acid to water, one of the hydrogens dissociates, and the K value for this reaction, this dissociation, is enormous. The K value is so big that the equilibrium lies almost entirely to the right, and there's very little molecular sulfuric acid left over. Most of it has been converted into ions. The HSO4- that remains is also acidic, and it can lose its acidic hydrogen. And this reaction, this equilibrium reaction you'll notice now, has a K value. And that K value is still pretty big, but it's considerably smaller than the first one. And we can consider another fairly common example, phosphoric acid. And so just like sulfuric acid, the first Ka, the Ka for the dissociation of that first acidic hydrogen, is relatively large, 7.5 times 10 to the minus 3. This would be an example of a fairly strong weak acid. But as you remove a proton, the Kas become subsequently smaller and smaller, so that by the time you get to the third Ka, that is the third dissociation, that final hydrogen is hardly acidic at all. And this trend is always going to be true for polyprotic acids. The first proton is always going to be easiest to remove, so its Ka will always be the largest. And then subsequent Kas will get smaller and smaller because the protons will be harder to remove. If you want to do accurate pH calculations with polyprotic acids, it's a little bit more complicated than doing calculations with monoprotic weak acids. And it requires a series of ice tables that involve the common ion effect. Although often you can perform only the first ice table calculation because the K values for the second ionizations and third ionizations are typically tiny. So we'll give you an example using a generic weak acid. If you want to calculate the pH of an H2a solution, that is some generic polyprotic weak acid, as long as you know the initial concentration and the K values, you can do this using an ice table. If you initially start with some water and you dump in enough H2a to reach a concentration of 0.1 molar, you can work out the equilibrium concentrations of H plus and HA-. And in a generic weak acid situation with a monoprotic acid, you could use that concentration of H plus and calculate the pH. But because you have a polyprotic acid, HA can also dissociate and contribute H plus ions to the solution, so you need a second ice table. And now the concentration of HA- is going to be the same one that you obtained from solving the first ice table. It'll just be X. And the H plus concentration will also be X. And your A2- concentration will be 0. And then you do a similar type of calculation to find the new equilibrium values. And while this process is not particularly complicated, it is a lot more work than for a monoprotic acid. The nice thing is that the second dissociation is almost always so small that it can be ignored. A common rule of thumb is that if the Ka for the second dissociation is more than 1,000 times smaller than the K for the first dissociation, then you can make the assumption that the vast majority of the H plus ion that will be produced by this acid dissociating is going to be produced by that first dissociation, which means once you find the H plus concentration from that first ice table, you can use that value to find the pH directly.